Hey guys, welcome back to our next lesson again. Today we're talking about algebra with functions. Our mindset message for today is that math makes sense. And I just want to remind you guys of that again. It's so easy to feel like math is this special subject that's only for some people. No, the reason why we have it as a required subject is because it is valuable for every single person. God's created us with a mind that can think and reason. And math has been created in a way that's supposed to make sense. You're going to have to work at it sometimes to make sense of it. It doesn't mean it's easy, of course. Our learning goals today, our main learning goal is just one pretty much, is to perform operations on functions and to learn about it a little deeper, but we're going to learn a new operation called composition. Prior knowledge basically would just be using function notation and domain and range. And we have already done some operations on functions up to this point, but we're like officially talking about it, I suppose, today. So let's dive right in. Our main idea today is that functions are objects we can perform operations on, just like numbers. Now, you remember that functions don't have to be defined using numbers. We've talked about functions before that don't necessarily use numbers in them. But we're mostly focusing in this course on functions that use numbers. And so it does make sense for us to think about performing operations on them. So this very first thing, just going to be a little bit of a warm-up, but we're going to talk about some specifics that maybe we haven't talked about before. So given f of x and g of x, find the following. So here's our rule for f of x and our rule for g of x. What's f of x plus g of x? It's going to be a new function that results, right? Now, we can literally just write the two functions and add them together. 2 parentheses x minus 3 squared plus 5x plus 7. And there we go. There's a new function. It's represented the sum of all the outputs from the previous functions, right? When we talk about a function, we're basically talking about a collection of all outputs that would result from putting all the different inputs in, right? Now this did not say to put it in normal form, so we are okay leaving it like this. I want to make a point for you on that. Unless there's a reason to put it in normal form, then we generally don't necessarily need to do that. But just purely for practice right now, because it's good to get that algebraic practice with manipulating things, why don't you go ahead and pause and actually expand this x minus 3 squared all out and put it into normal form real quick. So let's just check and make sure that you remember this. We expanded this, distribute the 2 in afterwards. Remember, you cannot distribute the 2 first. A couple of those things that people sometimes make mistakes on. And then we combine like terms. So in the end, in normal form, f of x plus g of x is 2x squared minus 7x plus 25. So the next two pieces here, I put these here just purely for notation, because you might see this and you might see this sometimes. Technically speaking, it is always true that if I have f of 2 plus g of 2, it's the same as f plus g of 2. Now, you might be wondering, what does that even mean, Mr. Engel? Maybe this looks confusing. Well, I wrote it in here. This just means plug in 2 to the function separately first and then add the outputs together. But this one means actually add the functions together first and then plug in that 2 to the sum function. Now, you and I both probably agree that we expect that to be the same. Now, we already did the sum function. So what we mean is, for part A, plug in separately to these and then add the results. And then for part B, just plug 2 straight into the sum function we found. Go ahead and do that yourselves, and let's confirm that we really do get the same output. Okay, just a quick work check here. If we plug this in, this becomes negative 1 squared, so that's 1. And 2 plus 10 plus 7 gives me 19. And then for this, using the sum function we found, 2 times 2 squared, that gives me 4 times 2. So 8 minus 14 is negative 6, plus 25 is also 19. And that's just like a confirmation. That's not proof. In fact, actually the proof we got was this right here, right? We actually did the algebraic work to show that this is the sum function, and we know the algebra works and that this must be identical because we use the rules that we already know. But this is just an important thing to help remind you guys again that for functions, whether we do the inputs first and then add, or if we add the functions first and then plug an input in, we're always just going to get the same result. And the same thing works for multiplication and subtraction and division, those main four operations. Okay, so a quick side note for you guys. This is just summarizing what we just said. If you see f plus g of x, it's the same as saying f of x plus g of x, and similarly for subtraction, multiplication, and division. So if you want to pause this and just jot these down, this is kind of an important thing, just to make sure you understand the notation that's used, and that these are just equivalent things, but different order. Okay, so a vocabulary for now. We're going to define it more formally later on, but we can use an entire function as the input for another function, and this is called the composition. Now, we're going to get into a little bit more of what this means, but an example will help us. We're going to use a function that's not numerical just to get us the idea of what's going on here. So let's say m of x is the name of person x's mother. So m for mother, a of x equals the age of person x. So for example, m of Ingle, my mother's name is Karen. And that's typical, but she's not a Karen, just in case you were wondering. And a of Ingle, my age, and I don't mind sharing, is 34. Although now that I think about how I define this function, I may have a problem because for any of you who watch this, this video like in future years, I won't be 34 anymore. Maybe there's a better way that we can define this function. Okay, hopefully you understood why that definition before was a little bit problematic for the age function. Instead, I'll say year of birth for person x, because that's always going to be the same for a specific person, right? Because we don't want it to be changing. So a of Ingle would be 1986. Okay? But here's what we're going to do next. We're actually going to put these two functions together and talk about what they mean in that context. Okay, so here's where we get to part C. Now this is like layered, you can think of it like a layered function, right? You can peel back the layers. So this says a of m of Ingle. We want to find that. And with that, you can just read it literally. It's the birth year of the mother of Ingle, because A is the birth year, M is the mother, and you can just read it like that. Now it's important to think about something here, because I put different interpretations. If I take Ingle and I apply M, then my mother's name is Karen, and then I apply A, her birth year was 1957. And I think about it in these diagrams, or sometimes we've learned functions like they're a machine that takes an input and alters it and puts out an output. So these are basically the same idea as each other. It is weird because sometimes students accidentally apply this in the wrong order. You have to think inside out, okay? It's A of M of Ingle. So I have to take Ingle and then apply M to it, right? And then I have to take the A function and apply it to whatever I got from that, right? So essentially, one function's output becomes the input for another function. Does that make sense? So either way, the final answer of A of M of Ingle is 1957, because it's Ingle's mother's year of birth. So what if we reversed the order of this, and instead I wanted to know what's M of A of Ingle? Well, again, think about what this question's asking. We're asking Ingle's year of birth and the mother of that year of birth. The mother of the birth year of Ingle. You probably realize along with me right now that that doesn't make any sense right now. Okay, so this just doesn't exist, I guess. That's the best way to say it. It does not exist. Doesn't make any sense. So here's one important thing about this composition operation. You don't get the same thing when you reverse it, even if you can calculate it, but a lot of times, if you reverse it, you can't calculate it in the first place. So maybe one direction it works, and the other direction it just doesn't work. But a lot of times, even if you flip the direction, you don't get the same thing necessarily. Let's take a look at some numerical functions where we have a composition.